here's the situation. Suppose you have n objects and you wish to choose k of them, all at once and not in any particular order. How many ways can this be done? Before I give you the answer, I want to make it clear exactly what I'm talking about. Suppose you have 3 objects. I don't know what they are. They could be books, they could be students, they could be anything you want. But let's just say that we've got 3 objects. Object 1, object 2, and object 3. Okay? So this is like the total collection of the objects that I have. And let's suppose that I just want to choose 2 of these objects. Okay? And the question is, how many ways can I choose 2 of them? And I really want to emphasize that when I say choose 2 of them, I mean choose 2 of them without imposing any particular order on the objects. I'm not saying designate one of these guys as the first object and designate another one of them as the second object. I don't want to designate anything as being first or second. I just want to have an unordered collection of 2 objects. What I mean by that is if you decide to choose objects 1 and 2, that's the same thing as choosing objects 2 and 1. Okay, so when I say choosing 2 of them without imposing any particular order, what I'm saying is just picking 2 of them. Not saying, oh, this is the first one and this is the second one, but just choosing an unordered collection. So what I want to do is I want to regard choosing 1 and 2 as the same thing as choosing 2 and 1. Similarly, I want to regard choosing 2 and 3 as the same thing as choosing 3 and 2, because we don't care about order. Regarded as unordered collections, this unordered collection is the same as this unordered collection. Okay? So how many ways can you do this? It's rather tricky, because any algorithm you're likely to write down probably overcounts. One reasonable algorithm might be step 1, choose the first object, and step 2, choose the second object. You can already tell, perhaps, that this algorithm is going to give the wrong answer, because even if you look at the language I'm using, I am inadvertently labeling one of my objects as the first object and another object as the second object. But I don't want to do that. I don't want a first object and a second object. I just want 2 objects, no order. So you can maybe already see that this algorithm is going to give you the wrong number, and sure enough it does. If we followed this algorithm, what would happen? Choose the first object. How many choices? Well, there's 3 objects, so naturally we have 3 choices, right? So 3 choices, and then choose the second object. How many choices? Well, since we've already chosen one of them, we now have 2 choices. That would give you 3 times 2, which is 6. I'm telling you that that is the wrong answer. Okay, that is definitely the wrong answer. This example is small enough that we can actually write down all the possibilities manually. So how many possibilities are there actually? Well, let's see. I could do 1 and 2, right? I could do 1 and 3, or I could do 2 and 3. And if you think about it, that's it. That's it. Because any other combination of 2 objects is already accounted for. You could say, oh, well, what about 2, 1? But remember, I'm regarding 2, 1 as the same thing as 1, 2. I don't care about the order, right? So there are actually only 3 possibilities. This algorithm overcounts the number of possibilities by a factor of 2. It's twice the correct number. Now, if you really think about why that's happening, basically what's happening is every one of these genuinely different outcomes is getting counted twice by this algorithm. Okay, let's think about the outcome 2, 3. Okay, the outcome 2, 3 is actually counted twice by this algorithm. Okay, here are 2 ways that the algorithm generates this outcome. For your first object, you could say For your first object, choose 2 as your first object. And then in step 2, what's your second object? You could say choose 3. That'll give you 2, 3. Or step 1, you could choose 3 as your quote-unquote first object. And step 2, choose 2 as your second object. Now, since we actually don't care about the order, and since we're regarding 2, 3 as the same thing as 3, 2, these two outcomes are actually identical. And so this algorithm is producing this same algorithm twice. It is overcounting the number of possibilities. Now, that was kind of a cute, small example with a few numbers, but we really have to think about, how to do this in general. And the real answer is the following. First of all, let me give you the answer, okay? And this is really what you need to know. The number of ways of choosing k objects from n objects is given by this formula right here. It's n factorial over k factorial times n minus k factorial. And I want to mention that this expression, this formula, comes up so often that we actually have some different notations for it. One notation is this guy right here. It's like a big C with the n on the bottom left and the k on the bottom right. That's one notation for this expression. You'll also see this. Different notation, but it means the same thing as the first one. It's like a big set of parentheses with n up top and k down below. It's kind of like a fraction, except there's no fraction bar. At any rate, they both mean the same thing. They both mean this formula here. They both represent the number of ways of choosing k objects out of n objects where order doesn't matter, okay? And they're both pronounced n choose k, all right? You'll see both of these notations. I think that this is probably a little more common in high school level textbooks, but this is much more common everywhere else on the planet. So, I'm going to use this one. It's also just a much cleaner and less cumbersome notation than this. This is kind of a weird notation. I don't like it. Anyway, I want to explain why this works. Why does this formula give you the correct number? So, what we're basically going to do is we're going to use a bad algorithm that overcounts the number of possibilities, which is kind of what we did with this algorithm here. But then what we'll do is we'll say, oh, this overcounts the number of possibilities, and we're going to fix it by dividing by the overcount to sort of compensate. That's the basic idea. Now, so here's an algorithm for counting the number of ways of choosing k objects out of n objects, all right? Now, it's a bad algorithm, as we're going to see. It overcounts, but let's just run through it. So step 1 is choose the first object. Well, there are n total objects, so you've got n choices. Step 2, choose the second object. Well, now there are only n minus 1 choices. Step 3, choose the right, and you just keep going, you keep choosing. And remember, we're trying to choose k objects, so you finally get down to the last step, which is step number k, and you choose the kth object. And how many choices are there? It's actually n minus k plus 1. If you notice, the number that appears here is, it's not exactly n minus this number. It's n minus this number plus 1, like n minus step 2, n minus 2 plus 1 is n minus 1. This number here is not n minus the step number, it's n minus the step number plus 1. That's why this is n minus, step k plus 1. Okay, that's just consistent. So if you used this algorithm, you would multiply all these guys together, n minus 1, all the way down, n minus k plus 1, and that would give you this expression here. It turns out this can be represented using factorial notation. So n times n minus 1 all the way up to n minus k plus 1 is actually the same thing as n factorial over n minus k factorial. If you write out the expansion of each of those guys, you'll see that most of the stuff cancels, and you'll be left with exactly this expression here. Now, the thing is, this guy overcounts, right? Because as you can see in the algorithm, it is sort of incorrectly designating some object as the first object and another object as the second object, when, remember, we're trying to count the number of unordered collections, right, of k objects. This thing is artificially imposing an order that we don't want to impose. And so, just like before on this sheet here, this algorithm treated 2, 3 as being different from 3, 2 when actually they're the same. This thing is overcounting. And so what we have to do is ask, by how much does it overcount? Well, basically, every given outcome gets overcounted by the same amount. So, let's suppose that we have a single outcome, all right, and let's say that you have the outcome 1, 2, 3, all the way up to k, all right? So that's k objects, right? How many times does this particular outcome get counted? Well, it gets counted once in this form, and it gets counted again as 2, 1, 3, if you just switch the 2 and the 1 all the way up to k. That's another way that it gets counted. It also gets counted as, say, 3, 2, 1, and then all the other numbers up to k. Basically, for every permutation, every rearrangement of this expression, the algorithm counts that object once. And so therefore, the number of times that this outcome gets counted is exactly the number of permutations of this expression, the number of rearrangements. Now, the number of permutations, the number of rearrangements of this expression is exactly k factorial. Okay? So therefore, this algorithm overcounts the number of possibilities by a factor of k factorial. So what we do is we take the number generated by this algorithm and then we divide it by k factorial. Okay, and that gives us the formula right here. Now, that's a pretty technical explanation of where this formula comes from. I think it's good for you to see, but I don't want you to panic, because the truth is that you can pretty much use these things without really fully understanding every line of that argument. As you'll see, the exercises we do are not remotely as abstract and crazy as the derivation and explanation that I just did. So let's talk about when to use choose numbers, okay? Whenever you want to simply choose some objects from some larger collection without imposing any order on them, you must use a choose number, okay? Sometimes it's hard to tell when you're looking at something that should be ordered and when it isn't. So I've given you a bunch of examples. So here are some examples of collections that are ordered, and then here are collections that are not ordered, okay? Collections that are ordered, what that means is changing the order of the objects results in a meaningfully different collection. Over here, collections which aren't ordered, changing the order results in a collection which is essentially the same as the original, okay? So here are some examples. An ordered example would be books on a shelf, okay? There's an order there. If you switch around the order of the books, that is a different configuration. If I walk into the library and if I rearrange all the books on the shelves, someone's going to notice, okay? So order matters in that situation. An example where order doesn't matter is ingredients on a pizza, right? If you say, I want pepperoni and anchovies, that's the same thing as saying I want anchovies and pepperoni, right? Order doesn't matter there. Here's a situation where order does matter. Students at a seating arrangement, right? If I switch around the people and where they sit in the room, surely people are going to notice. An example where order doesn't matter, this comes up a lot, is people on a team. Okay, so if the New England Patriots walk out, on the field and you point to the group and you say, oh, there's the New England Patriots, right? And then the Patriots walk around a little bit and then, suddenly they're sort of placed differently on the field. If you point to them, it's still the New England Patriots, right? It doesn't matter if Tom Brady is on the left or the right, it's still the same team, okay? So teams are a really good example of an unordered collection, a collection where order doesn't matter. An example where order does matter, different letters in a word. Okay, if you change the order of letters in a word, that's a different word, right? So order matters. A similar example where order doesn't matter is identical letters in a word. If you have a word with multiple identical letters, if you like switch the location of two identical e's, well, that's the same word, isn't it? So, yeah. Or how about different digits in the number? If you switch two different digits in a number, well, that's going to give you a different number. But if you switch two identical digits, like 1 5 here and another 5 here, and you switch them, well, obviously that's the same number, right? Here's a final example, an example where order does matter. People occupying different jobs, like one president, a vice president, and then a treasurer, versus people occupying identical positions. That's a situation where order doesn't matter. The basic idea behind that job thing is kind of like, you know, if I write down 3 people, like Billy, Bob, and Blob, okay, if these are 3 different positions, like president, vice president, and treasurer, if I switch around the order of the names, then you get a genuinely different configuration, right? I switched around these 2 people. Previously, Billy was president and Bob was VP. Now, Bob is president and Billy is vice president. That's a different configuration. On the other hand, if all 3 people occupy the same identical position, like if they're all just, you know, committee members, or if they're all just representatives, like Representative Billy, Representative Bob, and Representative Blob, if you switch the order of the names, well, because the positions are identical, you're looking at the same configuration. So that's the explanation there. Okay, so I just want to do, you know, probably a couple of examples here just to show you how straightforward this actually is, despite all of the sort of abstract stuff. So use a choose number to answer each question. So number 1, in how many ways can you choose a 3-person team from a group of 7 people? Well, all you're doing is you're choosing 3 people out of 7. Okay, you're choosing 3 objects out of 7 objects. How many ways are there of doing that? That's 7 choose 3, which by the definition of the factorial expression, it's, you know, basically the top number factorial over the bottom number factorial times the difference between them factorial. Oops, 7 minus 3 factorial. Okay, so you just have to go and compute this, and you'll get the appropriate answer. Okay, and why is this? Why are you using a choose number here? Because in a team, order doesn't matter, right? The team Billy, Bob, and Blob is the same team as Blob, Bob, and Billy. The order doesn't matter. Number 2, 10 people play a lottery. 4 people are to be awarded identical prizes. And how many ways can the 4 identical prizes be awarded? Well, you know, because the prizes are identical, all you really have to do is choose 4 winners, right? You're not saying there's a first place prize and a second place prize and a third place prize. There's no order on the winners. It's just there are 4 winners who occupy identical positions. So what you have to do is count the number of ways of choosing 4 people out of 10 people without ordering them. And the number of ways of doing that is exactly 10 choose 4, which using the factorial formula would be it's top number factorial over bottom number factorial times the difference between them factorial. And I'll let you simplify these on your own. I don't think you need me to do this in a video. You know, maybe just one more. A company wishes to hire 2 shift managers. The 2 positions are identical. There are 5 applicants. In how many ways can they hire 2 of the applicants for this position? Well, because the 2 positions are identical, really all they have to do is just choose 2 people to hire, right? It's like you're hiring one person for, you know, one position and then a different person for a different position. You just have to select 2 people. So that would be 5 choose 2. Okay, which is top number factorial over bottom number factorial times the difference between them factorial, whatever that winds up being.